Let's explore the two primary methodologies used to design and structure computer programs. Understanding this distinction is fundamental to modern software engineering. First, we have the procedural-oriented approach. In this model, a program is organized entirely around procedures or functions. Think of these as a series of computational action steps that need to be carried out. Look at the structure here on the left. We start with a central main function, which acts as the entry point of the entire program. When a problem is too big to handle at once, we decompose that complex problem into smaller tasks. You can see the main task splitting off into specific subtasks handled by function 1, function 2, and function 3. In this procedural world, the focus is strictly on the actions, the functions that process the data. Now let's contrast that with the object-oriented approach. Instead of a series of raw, disconnected functions, this system is structured around data or objects, modeling real-world entities. Notice how our main task here now branches out into organized classes. We have class 1, class 2, and class 3. What makes this special? Each of these classes encapsulates both the data and the methods used to manipulate that data together. This means that instead of a function existing in isolation, it belongs directly to the entity it is modifying. So the core difference boils down to this. A procedural language focuses on functions to decompose problems, while an object-oriented language focuses on modeling data and objects. Before we dive deeper into object-oriented programming, it is really necessary to understand the limitations of the procedural approach when working on large-scale engineering projects. Why did we need to switch? First, there is the issue of code reuse. In procedural programming, adding a new task often requires writing an entirely fresh set of functions, even if the underlying logic is similar. This naturally leads to a massive amount of redundancy. Second, debugging becomes incredibly difficult as the system grows. Because functions often share global data, an error in one part of the code can easily propagate across many other functions. Finding the root cause means examining every related procedure, which is incredibly time-consuming. Third, the system faces massive scalability issues. When a codebase grows to between 10,000 and 100,000 lines, developers lose control over the tangled interactions between functions. This makes the software very hard to update without breaking existing features. Finally, procedural programming can result in unnatural modeling. Real-world entities like a bank account or a car engine do not exist as mere sequences of steps. They possess unique properties and behaviors. Forcing these rich entities into a function-only paradigm always leads to awkward and complex code structures. The key takeaway here is that while procedural coding is great for simple math steps, large robust systems require the encapsulated real-world modeling of the object-oriented approach. To solve these limitations, we need to understand the fundamental building blocks that make up this new paradigm.
Object-oriented programming is built upon four main pillars. But before we look at those, let's start with the fundamental building blocks, which are classes and objects. An object is defined as anything that physically exists in the real world and can be distinguished from other things. For example, it could be a specific car, it could be a table, or it could be a specific person. These are tangible entities. A class, on the other hand, is completely conceptual. It is essentially a blueprint or a template. It groups objects that share common traits. For instance, person is a class. It defines what a person is conceptually, but you cannot talk to the concept of a person. You can only talk to a specific object of that class, like this specific person named Raju. Inside a class, we define attributes which represent the data or variables like name or age. And we define actions, which are the methods or functions that the entity can perform. Let's look at this Python code for a person class. We define the blueprint, set some attributes like name and age, and create a method called talk. Notice the word self here. This is a reference to the current instance of the object, allowing the method to access its own specific data. When we create an instance, we are building a real object based on that blueprint. Now let's move to our first major pillar, encapsulation. This is the mechanism of bundling data and the methods that operate on that data into a single cohesive unit, which we call a class. This acts like a protective lock, preventing outside code from directly accessing the internal workings of an object, which ensures data integrity. Looking at the student class example, you can see how variables and methods are grouped. There is a special method called init, which acts as our constructor. It is automatically called when a new object is created to set up the initial state. By bundling the data and the display method together, the program treats the student as a single unit rather than a mess of disconnected variables. Next is abstraction. This is the process of hiding irrelevant or sensitive details while exposing only the necessary information to the user. As a user, you just want to interact with the high-level interface without needing to understand the complex hidden implementation details behind the scenes. In Python, abstraction is often handled through naming conventions. Look at this bank class. It has public information like account number and balance that a bank clerk can see. However, the loan amount has an underscore in front of it. This underscore tells other developers that this is sensitive data meant to be kept private and hidden from standard view. Moving to the top right, we have inheritance. This allows a new class to derive attributes and methods from an existing class. It creates a hierarchy where a derived class like class B gets all the functionality of class A plus whatever new features it adds itself. The massive benefit here is code reuse, which drastically reduces development effort. The final pillar is polymorphism, which simply means many forms. It allows a single interface to behave differently based on the input it receives. For example, if we use an add function with two numbers like 5 and 10, it performs mathematical addition to give us 15. But if we use that exact same function with two strings like core and Python, it changes its behavior to concatenate them into a single string. It automatically adapts to the data type. To wrap up, let's look at Python's overall role in this. Python sits in a unique flexible position. It fully supports traditional procedural programming focused on functions, as well as the complete object-oriented approach focused on classes. It lets you choose the best tool for the job. So, whenever you are designing a system, remember these core ideas. Procedural relies on functions, object-oriented relies on objects, encapsulation protects your data, abstraction simplifies your interface, inheritance promotes code reuse, and polymorphism gives your code flexible, adaptable behavior.